Thank you very much for this invitation. And indeed, I will present you our work on the understanding on old masters painting techniques. And what we do in the labs, we study different, we study cultural heritage in a broad sense, but we have specialists in paint and polychromy, pharmacy and cosmetics, or biomaterials. And I'm more specialized in paint and polychromy. That's why I will focus my talk here on paint and polychromy. So we can have different motivation when we study works of art. First, we all want to gain knowledge on art history and techniques. Sometimes the information we get can help the curator and the restorers to better preserve and restore the paintings. And in some cases, it can help also to authentify and date the works of art. So I will first give you, it's a famous example of a painting that was sold like 3 million euros. It was dated on 1914. So before the First World War, supposed to have been painted by Heinrich Kempendock. I don't know how to pronounce it, sorry. So it's an expressionist painter. And in fact, they did some analysis of the pigment, and they found that the white pigment is titanium white pigment that was synthesized for the first time long after this date. So this painting was a fake, and the famous painter, now famous, his name is Beltracchi. So he was found guilty for 14 paintings, but he claimed that he has faked more than 50 artists. So this means that there are still in European museums fakes from Beltracchi. So we don't have so many cases like this, but sometimes it comes. And so what we do first is, first of all, we look at all the pigment that the artist has used. It's the most simple analysis, I would say. And then we can go further and try to understand not only the list of pigments, but how the artist used the pigments and the recipe that he used. In some cases, we want to have information on where the pigment comes from. And also the long-term evolution of the material. This for restoration issues. So I will present you first what we do directly on the works of art. So the LAMS is located in Jussieu, close to here. And so we are not in a museum. So we built instruments to go inside the museum or in archaeological place and to investigate the works of art where they are. So we work with in situ portable instruments, and I will show you different examples where we did simple qualitative analysis, I would call it, and what we can get just from the pigment identification. In some cases, we want to go further and do quantitative analysis, and this will be illustrated by my PhD work about Leonardo da Vinci. And now, new development, we're trying to develop imaging techniques to get also more information. And then the second part of my work, which takes place in a chemistry lab, is that we do reconstruction of the old recipe, and then we investigate the property of the paint material. So we can get also complementary information from this kind of work. So first of all, what we can do on an historical painting, first we have to look at it. Okay, it's the first thing that I have been told when I was starting my PhD. Don't start with the experiment. Just first, you have to spend hours looking at the painting. So under optical microscope, then under different radiation, photographs, infrared reflectography, and also then with the X-ray radiography and emissography. These are really very simple measurements and imaging that are used in the Louvre Museum, for example. And then we can do local measurements, invasive analysis or non-invasive analysis. And as you can understand on some precious works of art, we cannot do sampling just very easy, so we don't want to do, and usually we are not allowed to do. So we have to focus on the development on this kind of analysis. When we have big questions that cannot be answered by in situ analysis, then we can ask for a sample. So it's really micro-sampling. You don't see anything with the eye. And then you can either analyze it in a non-destructive way or do more destructive analysis, but this will be really the final step. So, as I will focus on the non-invasive analysis, just to remind you that a paint is made of a pigment mixed with a binder. So it can be oil if it's oil painting, it can be water and egg if it's tempera painting. And then you have two parts in this paint, inorganic materials and organic materials. And as you will see, most of the technique we have until now allow the identification of the inorganic part of the painting. So I will focus on the pigment identification, but it's really a big field of research for now to better identify this organic part without taking a sample. So first of all, I want to show you what we can get from a very simple pigment identification. This was the curator in charge of this famous painting in Dublin. It's from Caravaggio, the Taking of Christ, and he was just curious about the masterpiece of his museum, and he wanted to know all the pigments that Caravaggio could have used. So what we did is we've been there with our portable instrument, combining X-ray diffraction and X-ray fluorescence analysis. So with the X-ray fluorescence, you will get the main elements that are contained in the painting. And with X-ray diffraction, you can identify the compounds if it's a crystalline pigments. So combining those two techniques, you can really identify most of the pigments that are used here. So we did many points of analysis, and we could identify, for example, here on the green dress, it's a copper-based pigment, it's malachite, and here it's azurite. So with X-ray fluorescence, you just know that there is copper, and with X-ray diffraction, you identify the compound here. And what we could see that was quite surprising is that you see, so it's a very dark painting, and we were a bit surprised that the center of this painting, in the middle of the painting, there is this black armor of the soldier. So you don't really see what it is. It's very black everywhere. You just have white reflection. But we could find on all the points that we measure in the armor, we did find a lot of cobalt. And the cobalt can be linked to the use of a blue pigment, which is a smalt, that is known to fade with time in some conditions. So this painting was really not like this, in fact, when Caravaggio painted it. But we should add, in fact, a blue reflections and effects in this part. So with a simple qualitative analysis, sometimes we can reveal the intention, the first intention of the artist, and maybe help in a better preservation and restoration, because maybe this will help for the next restorer to look into it and check this degradation of smalt. In some cases, we want to go further in the understanding of the technique, because we have access to several paintings, for example, of the same painter. And we have a collaboration with a specialist of Nicolas Poussin, and she was really interested in the analysis that we could do on several paintings. So we're still going on with this study, but we already investigated 3 of them. So 2 are in the Museum of Rouen. Sorry, it's again quite a dark painting. And then is in the Fitzwilliam Museum in Cambridge. So we did here again X-ray fluorescence and X-ray diffraction analysis. And what we have shown is the use of the pigments that Nicolas Poussin made. So it's a very restricted list of pigments. And what was quite striking is that this pigment, okay, this mineral is lazurite, is a main compound of the pigment lapis lazuli. And maybe you know that lapis lazuli is a very precious pigment. It's a pigment that is used at Renaissance time for the blue dress of the Virgin. So you use a cheap pigment for the sky, and then for the dress you use lapis lazuli. But here, Nicolas Poussin used lapis lazuli everywhere. So in the dress here, but also in the sky, and also as a mixture mixed with yellow in the green landscape, and everywhere here also and here also. And this lapis lazuli was really used in in a philosophical point of view by Nicolas Poussin. He wanted to show the unity between the creation and the human beings. So it's not only a technical, he wanted blue, he used blue pigment, but it's really that he puts his philosophy in the paintings. And then if we wanted to go further, so we investigated this painting, which represents a storm. And we wanted to see the shadows effects that he could achieve here in this painting. So we compared the image of, so you see, I don't know if you really see well, but it's a house, and there is a tree, a window, and the shadow in the wall. And if you can compare it, sorry, you can compare with the X-ray radiography and the infrared reflectography here on the right. And we did some X-ray fluorescence measurement on the red line that I indicated here. So what you can immediately see, I will show it here. What you can see is that on the tree, the X-ray radiography is really, really dark. Shows a black spot here, whereas the window appears in white. So depending on the shadow and the effect you wanted, he didn't use the same painting techniques. And we did some, thank you. And we did so with some X-ray fluorescence measurements to identify the pigment too. And what we could see is that he used for the window a specific pigment. He used carbon black, whereas he used bone black for the tree and for the shadow here. And if you discuss with art historians, they will tell you that carbon black is more bluish than it is used for the sky, and the window is opening to the sky, so it's logical. And we were, yes, but it's a very tiny, tiny zone in the painting, and he has used 3 different pigments for the shadow. So maybe some of you think we are interpreting too much the result of the analysis that we have. But in the case of Nicolas Poussin, he is a painter who said, I have neglected nothing. And we know that he has read all Leonardo da Vinci painting treatises, because he illustrated them. And we know that he was interested in philosophy and the theory of painting. So he has neglected nothing, means really he was choosing each pigment he was using.
Excuse me, the 2 black pictures, middle and right, are made by reflection, not transmission.
This was X-ray transmission. Yeah.
Transmission,
yeah.
This one?
And this one, we didn't do it. It's a infrared reflectography from the museum, not from us. Yeah. So I go to my next example, which is Leonardo da Vinci. So in some cases, qualitative analysis is not enough. It will, in the case of Leonardo da Vinci, just give you the information that he used earth pigments to model the shadow, and it's not enough to understand his technique. So my PhD was about the famous sfumato technique of Leonardo da Vinci. Sfumato comes from the word fumare, smoke in Italian, and it expresses the effects that Leonardo da Vinci could obtain on his painting. So everything is smooth. I don't know if you see this here, but there is no limit, no brush strokes, and the impression is very, very smooth. He really models the shadow. This is, you recognize it, it's the famous face of Mona Lisa, and we were interested in how could he achieve such effect, and especially on these faces. So on those kind of paintings, and especially on this face, you cannot ask for a sample. So you have to try to get as much information as you can with the in situ experiments that you have. So what we did was X-ray fluorescence. So, and it was just for a routine experiment, just to know what was the pigment inside. So as in a qualitative way, so you get characteristic lines at different energies, and this is, depending on the energy, it indicates you the elements which are present. So you have, for example, here, the low energy line for lead, and because Leonardo da Vinci used lead white in his paintings. That's a simple way to interpret those data. But then, if you want to go further, you can try to correlate, and it's correlated. Okay, the area and the intensity of each line, each peak, is linked to the concentration and to the amount of pigment that was used. So for a homogeneous sample, so for example, if you take a ceramic and which will be completely homogeneous, then you can have quantitative analysis easily. But in the case of a painting, and especially this kind of paintings, it's a multi-layer material. So you have to take into account the X-ray penetration and the absorption by the varnish first and the other layers. So to interpret the data and the spectrum we did, we made this kind of hypothesis. So first we have the wood panel, this we know. Then there is this gesso layer, which is a layer that prepares the wood to receive the oil painting. Otherwise, if you put oil on the wood, it will be completely absorbed. So you put gesso, which is a calcium sulfate with glue. Then this layer is made of lead white and oil. Then there is a layer probably pink with a small amount of vermilion pigment, which is red and mixed with lead white, so it's pink, to give the color of the face. And then we had two assumptions for the shadow. Either it's a dark paint that he has added like this, or either he could use dark glaze. A glaze is a very thin translucent layer, so made with a very small amount of pigment and a large part of binder. And so you can superimpose the glaze to obtain very smooth effect, as Leonardo could do. So that was the hypothesis for the data treatment. So what was done was a line on the face of Mona Lisa from the clear part of her face to the shadow here. And what you can see here, that there is nearly no manganese and iron, which are elements that will be present in an earth pigment used for the shadow. And there is this M line of lead that is really interesting for us because it's very low in energy, it's very sensitive to the absorption. And what we could see is that when you go further in the shadow, then you see the increase of manganese and iron, which is normal because it was used to model the shadow. It's the earth pigment. And then you see the decrease of the M line of lead, indicating an increase of the absorption by the upper layer. So this was confirming the hypothesis of a glaze layer of which the thickness is increasing in the shadow.
Is the spot representative of your
it's a bit big. No, it's a bit like this. It's 1-2 millimeters, the spot that we have with X-ray fluorescence. So, yeah, it's a bit bigger, I think. Yeah. So we had to simulate the spectrum and the old lines that we have, taking into account all the steps of the X-ray beam, of the X-ray beam path, and taking into account the absorption of the X-rays through the different layers of varnish first and glaze. And by doing this, I didn't write it here, but we use software made at ESRF. So normally it's used for a monochromatic beam, but here it was extended to our polychromatic beam. And so we could simulate and estimate the thickness of the various layers. So the lead white layer, which is approximately around 50 micrometers. And I say this because the X-ray beam then can be stopped in the lead white layer. You don't access to the gesso. And then this was a more striking result because we could see that the first glaze layer was around 2-3 micrometers. And then you had to superimpose like 20 layers to achieve this kind of thickness here and to model the shadow. And maybe you know that when you paint a glaze, so you had to paint first and then you had to wait because it's oil painting and it takes a long time to dry. He had to wait for like 2 weeks before being able to apply another layer. That's why it's so long for him to paint such a painting, and he didn't paint it so much. So what we did, and this was all my PhD is the analysis of all the paintings that are in the Louvre Museum, and we could see that on those three paintings that are really from the end of the life of Leonardo da Vinci, you have this kind of effect, so a strong absorption of the low energy line of lead, which indicates the use of glazes. Whereas in the other paintings, you don't have this kind of effect. You use just a paint, dark paint, to the shadow. And it's really the achievement of his life to paint like this and to use those kind of superposition of glazes. But I have to say that this kind of approach to do quantitative analysis on the painting, as you see, it was a PhD work, so it takes you 3 years to estimate what can be the thickness and what you could tell in the software so that you don't do mistakes in the hypothesis that you make. And so we don't do this for a random painting. So another approach also to get further information on paintings is, this in fact is an old schema. Now I could represent something binding the local and the global approach with imaging, chemical imaging techniques. So it's new development now. So in the lab we have mainly two instruments, two systems that allow imaging techniques. So first, the X-ray fluorescence imaging, a very simple system with the head here and mounted on two translation systems. So we have the image. And then we have two hyperspectral camera. So one in the visible range, so 400 to 1000, near infrared also. And the SWIR one from 1000 to 2500 nanometers. And the detector, it's a push brom system, so the detector is a line, and so you have to either translate it, either to rotate it to obtain the whole image. Usually we use a rotation system just because it's less heavy, but it gives you a deformation in the image that then you have to correct and so on. So the principle is that you will get images with each pixel linked to a spectrum that then you can interpret and understand the composition of the paintings. So just one example of what we can do here. So it's a simple example because it's a manuscript and then I don't have a varnish layer that would disturb my measurement. Here the image I obtained from the hyperspectral camera with a zoom optic. And then I can look at each color and see what is the pigment used thanks to the reflectance spectrum and the absorbance that we can calculate. And then, but doing like this, we also need statistical treatment, data treatment, because with this kind of imaging, then you get a lot of spectrum that you have to interpret and analyze. And then we use this kind of data treatment with doing segmentation. And then you can look at the image and recognize where the same pigment is used. And then you will have the end member spectrum that you can interpret. So this is a way we are still trying to find the best way for each kind of works of art, the best way to work on it. And so, for example, here we could identify the use of a lake on this dress, which was quite surprising because usually at this time it's vermilion. Mercury sulfide, which is normally used, but here it's a lake, and we know that this lake was in fact used to tint as a pictorial dye at this time for the dress. We compared all the pigments that was used in the main illumination to the pigments outside of the main illumination, and it's not the same choice. The main illumination was really more precious, and then you wanted to use specific pigments. And what we could see, for example, in this small apple is the use of vermilion compared to the red here. And I did this really because I had the image, because otherwise I would have never analyzed this apple. In this small apple, there are 4 pigments. So there is a vermilion, there is gold here to highlight the light. Then there is Brazil wood, so the same lake as in the main illumination, here for the shadow. And here in the hole, there is carbon black. So it's just to show that with imaging techniques, sometimes you can get information that you would have never think to have at the first place. Another example was in Barcelona. We analyzed paintings from the 15th century with a different camera, so visible, sphere, and also X-ray fluorescence mapping. And here the aim was to use this wavelength range from 1,000 to 2,500 to get an information on the binders that was used. Because at this time, it could be either egg yolk, either linseed oil. It was both used, and the curators really don't know. And we've seen that in the publication, some groups can achieve this identification of the binder, but they have shown it for manuscripts, so without a varnish, and between glue and oil, for example. Whereas here, we are in a tricky case, and we are still processing the data, so I don't have the answer yet, I'm sorry. But what we could see immediately, still in this wavelength range, is that old restorers made a mistake while restoring it at the 19th century. So they used carbon black in this area to restore it because the color looked completely black. Whereas here, our measurements have shown that it was not black, it was blue. And the X-ray fluorescence mapping confirmed it also. So azurite, which is a copper-based pigment, which is blue, was used here. And for some reasons, it becomes black, completely black. So this is the perfect transition for the second part of my talk, because sometimes the in situ analysis will bring results, sometimes, yeah, but also a lot of questions. And in that case, we were really surprised to see this strong degradation of the azurite. And when we compared, so those are macro photographies that we do always on the paintings that we analyze. Those two are of the same age. It's the 15th century, but this is from the manuscript, and this is from the painting in Barcelona. And you see the difference in the conservation of this color. So something happened. And this other is another degradation process on azurite, but it's the same binder as for the manuscript. So we are trying to find some clues to see which are the conditions that will give such degradation. So when we see this, and when we cannot have samples, but maybe we will ask for a sample on the Barcelona paintings if we find nice results in the lab. So we prepare mock-up samples and mixing the pigment with the egg or the pigment with the oil, and then we're doing aging experiments. So depending on the condition of aging, and some were really dramatic, we get more or less degradation. So the next step will be to analyze those results, to do some chemical measurement to understand what could happen and what are the compounds that are formed. Another example is that, so the Nicolas Poussin analysis brings also other questions, because I've told you that in some cases it's philosophical reason. You use pigment for a specific reason. In some other cases, there is no philosophy in it, so there must be a technical reason. And here we noticed in those three paintings an important use of calcite. We know that sometimes calcite is added to the pigment just because it's cheap, and then you can reduce the price. So it's used as an extender. But in that case, you have more or less calcite depending on the color and depending on the part of the painting. So we were interested in understanding how can it change the paint properties. So for this, you have to prepare paint. And I just wanted to emphasize this because it's really a difficult task for experimentalists to prepare the paint as they would have done it in a workshop. So, and we don't do it really as they were preparing it in the workshop, because here you have apprentices, so like a student at 13, 14 years old. And so they spent like 3 years just learning how to prepare the paint. And they were not allowed to touch the painting of the master. They were just allowed to prepare the paint as the master wanted it. So, and you can see here that they are really grinding the pigment in the oil. And depending on the pigments, you cannot grind it the same way and the same time and so on. But okay, we are trying to do it a bit more in a scientific way and reproducible way. So we just grind it in a mortar and then under the Muller for 3 minutes, okay, depending on the pigments, and to obtain, and it really changed the rheological property of the paint. So you cannot miss really this step. So what we saw by mixing the calcite and the lead white is that you can increase the transparency of the layer. So these are really very simple measurements when you apply it on a black dark support. So Nicolas Poussin may have used this increase in transparency. As he knew Leonardo da Vinci works on transparency, he was interested in this kind of effect. But in the case of other painters, like Rembrandt, it was also noticed in some publication that the use of calcite was really important. And in the case of Rembrandt, there is no use of transparency. It's really opaque paint. And so what we were looking at is how this calcite can modify the rheological properties. And what we saw, we were looking at the yield stress. So the yield stress is the minimum force you have to apply on the paste to make it flow. So in a paint tube, for example, or for toothpaste, is how you have to press on it to make it flow. And you see that when you add calcite, in fact, the yield stress will increase. And then you can more easily obtain brush strokes and this kind of effects. If you paint with a very fluid paint, everything will be leveled and you will have something very smooth. Whereas if you paint with a very elastic paint, then you will get really strong impasto effect. Then my last example. At the 19th century, painters were trying new recipes, and because they were trying to paint in another way. So they wanted to achieve, to show and to express feelings and movement in their painting. So this painting is from William Turner. Sorry, I didn't write it here. And we know that he painted this painting in 3 days, which was really amazing for this time. When you think that Leonardo da Vinci could paint his painting for 3 years, here it's really a great achievement. But he could do this because he used new recipes at the time. And if you look in the recipe book, you will find this kind of mentions here. And if you translate it in a chemical point of view, then you will see that it's a mixture of resin and a lead compound and oil. So we were curious about this because we had in the lab oil prepared with lead, and we had in the lab varnish. So we're thinking, why not try and see if you really can get a gel doing this. So indeed, you get this kind of mixture. So we investigated to check the rheological properties. And what we could see was quite interesting. So these are the viscoelastic properties of the paint here and the gumption here. So the elastic modulus, which is here, is much higher than the viscous modulus for more than a decade of stress. Then when you mixed the gumption with the paint, you obtain much higher elastic modulus and viscous modulus. So the properties are not in the middle of both systems, but it's really enhanced. And if you don't really like rheological curves, you can just look at the picture here and see the effect of adding gumption. So for the painter, it was like magical. You can really modify and obtain strong impasto effects by using this. And as there is lead inside, you can also paint faster because it will dry faster. So that was described as the perfect medium. What we try to do next, and okay, it will be the beginning of a PhD right now, is to understand the chemistry of this system, but just how the gel is formed. So we investigated it on a mesoscale with mesoscale experiments. So here, freeze fracture electron microscopy that revealed that there are lamellas in a continuous phase. So yeah, we did also a spectroscopic measurements to try to understand the role of lead and so on. But as there are 31 molecules in the mastic resin, we have to go to a more simple system to get a proper understanding of what's happening in this. What was surprising also is that in all the recipe, you have the oil that is mentioned. But if you try, you will see that the varnish, the gel can be formed without oil, and that you don't need the oil in the recipe. So then we investigated also by spectroscopy the importance of radical mechanism in the gelification. So because we saw that adding tempo, which is a radical inhibitor, we didn't get gelification. So we did the hyperspectroscopy with spin trapping technique. And okay, I won't go into the details, but here we could see that after 40 minutes, after mixing the resin and the lead, there is a new radical species that is formed. So we propose some mechanism in this, and we can say that there is a radical cross-linking process, probably coupled with mesoscopic lamellar organization on those systems, which was what is amazing is that it was used by the 19th century painter in old England, and they really didn't know what they were doing just by mixing the oil and the varnish and the lead. But in fact, they were doing a gel with a radical mechanism and so on. And now we are trying to understand this because in some cases, the painter were not as lucky as William Turner. So maybe not lucky, but he knew how to use the gumption properly and to obtain this kind of effect. This Portuguese painter was more unfortunate, and you can see really dramatic effects. As there is lead inside and as it's secative for the painting, then if you use it a bit too much, if you use too much gumption, and if you want to be too fast, then you will get this kind of effect. So we are still trying to understand what was exactly the role of lead in this. Was it just a catalyst? Is it a bridging agent? So this is the next step of the research. But yeah, we hope to solve and to address those kind of questions. So I see that I was very fast. I wanted to conclude with a French citation of Pasteur, where he said that he sees directly in some cases the possible link between science and art, and where the chemist and the physician can take place close to the artist and enlighten them. And that's what I hope I could show you here. So thank you for your attention, and I have plenty of time for questions.
Is there any software to reconstruct, but in the computer, with all the information you have, take Gioconda and try to make it as close as possible to how it was the day after painted?
Until now, no. There is no software that will can regroup all the information together. But there were some measurements to reconstruct the visual appearance of Mona Lisa just after painting without the varnish. So these are just optical measurements, as we could do with a visible hyperspectral camera. And so based on optical calculation, we can remove the varnish and simulate how it was painted. Yeah.
This is on the web?
I don't know. I know that there was an exhibition in Paris. I don't know now where it is. There is a book on it. So I don't think they put it on the web because it's a book that is sold.
So one more thing. And with Caravaggio, what happened with the blue? Did somebody try to see it with the black that was blue? Is there any picture where it's more like it was?
In fact, for this study, we were a bit limited because it was the curator who asked us to come, and it was part of a European project. And so we were just like doing service for the museum. So we were stopped at this age, and we were saying, we are available if you want more information, but the curator just was okay with what he did. So, and he didn't propose us to take a sample. But the degradation of smalt is quite well known. So, and there are other studies on this to understand what could happen here. But the next step for me now would be to write to him and tell him, okay, now we have imaging techniques, and now we can have the whole image of your painting, and with the mapping of cobalt, then he will be really able to see the effects that could have been there with smalts.
A radical-induced jellification should be temperature sensitive. If you lower the temperature, you should reduce the rate. Has this been looked into?
We did several tests with the temperature, but it was quite problematic because here it's in turpentine, so the solvent, there is a solvent, and then you change the nature, the solvent evaporates a bit when I increase. So I couldn't increase until 70 degrees, and the gel was okay. But then it doesn't look the same after 70. It's more solid. There is, the solvent evaporates too much, so I couldn't see it.
Difficult to study.
Yeah.
I have a question about your safety limit of exposure to X-ray, which are very, very energetic photon. So as we know that pictures of the past are modified mostly by UV exposure, I suppose that you have, by law, some limit to apply such density of X-ray.
For us or for the painting? What,
no, not for your body, I don't care. Just for the painting. For the painting, I suppose that you focus rather close points, but at this place you have some radiation, and you add many, many very dangerous photons, which are X-ray photons, which are much worse than UV photons. So, can you say what are
the limitations,
intensity limits that are imposed to you to not to destroy too much?
The question is embarrassing because we don't have limitation. In fact, we know that we are at really low tension and intensity because we are under the regulation that are for us. I mean, we don't have to wear a dosimeter, so we are under this regulation, and so it's very low, and we know that the same paintings in the synchrotron, for example, would be damaged by the X-ray beam because the organic varnish layer would be really blackened here, and even the particle accelerator, gave, but it's another problem, gave dark impact points, but here. It's just the experience that say that in 30 years we don't have any damage, and it's a bit scary because my PhD supervisor was always telling me maybe in 50 years you will see black spots in Mona Lisa's face and it will be your fault. But I don't think so. We are really under the level of all regulation, in fact. So, and there is no specific regulation for art painting. So
because there are regulations for exposure to visible light. I have seen in the museum at Tokyo for the aquatint paintings. They are very small radiation of visible light, which is, by the way, under voltage lamps, so it's mostly red.
Curiously, when we are doing the hyperspectral with the camera hyperspectral, then we have to have two strong halogen lamps, and then the curators are much more worried with this light than when we do the X-ray measurements. But it's also because the lamp is heating a bit, so we have to place it quite far away and to reduce the measurement time and so on. For the X-ray, what I can say is that we are really low in tension and intensity, and also it's maximum 5 minutes of measurements, and then we change the point. So it's very limited on one spot. And the spot is 1-2 millimeters. It's not so focused also. Whereas, yeah.
I wanted to know to which extent the results that you, I mean, for example, the techniques that you uncover about how Leonardo da Vinci was painting the shadows and so on, were already known to art historians from contemporary written documents or so on, or and I mean about this one, but any kind of other analysis that you're doing, are you like really trying to work on stuff that people don't know, or sometimes you make links, or yeah, do you like discover stuff that nobody knew at all before?
In fact, it really depends on which painting you are working. On Leonardo da Vinci, I started my PhD and I saw so many things written on it. So, but we based our work on all what was done before. So this glaze technique that was an hypothesis from the art historian and the researcher was really the basis of our simulation of the spectra, and we couldn't have simulated anything if we hadn't this hypothesis of work. But we are also working on less well-known paintings, fortunately. And for example, I'm working currently on Himalayan works of art. And about this kind of painting, nothing is known on this region, and there is no written history about this kind of works of art. So we're trying to do both, and yeah. But it really depends on what you want. On the Himalayan works of art, I just identify the pigment, and this is already a big step for this kind of works of art. In the case of Mona Lisa, if I just identify the pigment, I do nothing. It's something already known. So yeah.
But do we know that Da Vinci had to really wait 2 weeks before he could paint the next layer? Because I have a friend who does this in a day, just with oil and pigment.
It's not written anywhere, but what is written is that he kept it unachieved for a very long time. I mean, people that were coming in his workshop saw this painting and didn't understand why he wasn't finishing it. So that can be an assumption that he just wanted it to be perfect, and so he was waiting to apply a new layer. But we don't know exactly. But one day with the technique of this time seems very short, because even if you take just linseed oil, and even if you prepare it with lead, in one day it's not dried, and okay, then you mix a bit with the layer that is under it. But yeah, so.
Dry in one day to touch it.
It's sticky, you know?
My friend prepares it, it's not sticky. I was surprised because
yeah.
Commercial paint is not dry.
So you prepare it in a specific way. Yeah, yeah. Yeah.
I'm amazed how quickly it dries.
Oh. But in the case of glaze, it's really, it's 90% oil. So maybe also it takes more time also to dry than lead white, for example, with oil. So if there is pigment, then you will have the impression it dries faster. But for the glaze, yeah, it's really oil, so it has to be well prepared. So they could increase the thicativity, so the drying properties, by adding lead or manganese. That was also an assumption. But
She doesn't do this.
oh, okay. So just yeah, it's interesting. Yeah.
Is the rather elaborate preparation of, for sfumato responsible for the cracks in the painting?
That was it's an interesting question. Sorry, I come back to the picture, the first one, because maybe you notice that on these parts, yeah, where there is the shadows, there are less cracks. Whereas, so the cracking pattern is not the same on all the panel, and so also the glaze, so the mixture used for the glaze had specific mechanical properties, and I tried. It was one thing I tried also during my PhD, is trying to understand how we could modify the mechanical properties by adding some ingredients in the glaze. Because that's a big question for restorers, because when you restore painting, you remove, yeah, you decrease the varnish thickness or you remove it, and then you can try to do something. And in the case of Leonardo da Vinci, there are those very thin glaze layers, and we don't know exactly what is a binder. So if the varnish has the same composition as the glaze, when you remove the varnish, then you will remove also the glaze. And that's why the restoration of Leonardo da Vinci is so complicated, and there are always a lot of discussion around it, because they are scared that if they remove the varnish, then they remove the glaze, and then all the effect is gone. But it answers to the question. Maybe I went to it. No. Okay.
Okay. When I am looking myself at the Poussin's paintings, immediately I recognize because of the yellow color.
Yeah.
So is it something typical of him for this yellow, or is he using the same technically as other painters of his time?
It's a I would say common pigment, because it's a lead tin oxide or lead tin antimony oxide, which is a common yellow pigment. But the thing is that he used only a few pigments, and the pure pigments. So it's always, as I said, it chooses properly the pigment. So it will always take pure ingredients. That's maybe why you notice it particularly compared to other painters that would use maybe the same kind but mix with earth or doing some strange mixtures. Here you really use in the proper way, I would say. So, but the pigment is quite well known for his time. Yeah.
So you could say this is really a genuine Poussin's because of the proportion of pure yellow in your analysis.
Yeah, I didn't focus so much on the yellow, so I don't want to go too far. But yeah, it's because it's also true for other pigments. So maybe the red also it's quite a precious one, and this yellow too. So it's a global use of pigments, I would say.